In this video, we're going to be looking at 111 equivalent representations of polynomial and rational functions. And this is our day 1 video. We're going to go ahead and just jump right into a problem here, a little bit of review of things that we've been looking at in the last few lessons. But here we have a function, a rational function, as we've seen several times recently. And we're given this function. This is the form we call standard form. They want us to go ahead and write this in factored form. So it's a process that we've been using for a little bit now with our rational functions. We're going to go ahead and write this in factored form. So in the numerator, I'm going to go ahead and factor out a2. Let's see. I think I'm actually going to do this down below here. So let's see, f of x equals 2x squared minus 4x minus 6 over x squared plus 3x plus 2. Alright, I'm factoring out that 2 in the numerator, leaving me with x squared minus 2x minus 3 over nothing to factor out there, so x squared plus 3x plus 2. And we go ahead and continue factoring. In the top, that should be x minus 3 and x plus 1. In the denominator, that should be x plus 2 and x plus 1. So this is, again, our standard form. And this is our factored form. So it says, so this was part A, and then it says in part B, identify the end behavior, vertical asymptotes, zeros, and wholes. Don't need to worry about limit notation, except for maybe the end behavior, but we want to identify that information. So, starting with the end behavior, this is using our powers here. So we look at our first terms, and we have y equals 2x squared over x squared. Well, that leaves us with just 2, those canceling out. So this means that we definitely have a horizontal asymptote at y equals 2. So that would be our end behavior. So our limits as x goes to, and I'm just going to go ahead and combine it, as x goes to positive and negative infinity for this function, it goes to 2. So that's what's happening as we go to both ends. All right. We also have our vertical asymptotes, so VAs. Actually, I usually like to find the wholes first, so I'm actually going to do that, wholes. And we do have wholes. Looking now at our factored form, we have that common pair there. So that would be x plus 1 equal to 0. So we have a whole at x equals negative 1. We can go ahead and plug that back into what's remaining to find the actual point. So that would be 2 times negative 1 minus 3, right? Negative 1 minus 3 over negative 1 plus 2. So that should give us 2 times negative 4 over positive 1, so negative 8. So we have a whole at negative 1 comma negative 8. Okay, and then vertical asymptotes of VAs. So using what's left in the denominator, the x plus 2 equal to 0. So we have vertical asymptote at x equals negative 2. And then zeros. What's remaining in the numerator would be x minus 3 equal to 0. So we have a 0 at x equals 3, or the point 3 comma 0. All right, so we're able to find each of that information from the standard and factored forms. So going on to problem B, we have a factored form here. We are given the factored form of G. So for part A, we're given the factored form, and they want us to identify the standard form. So we have 3 times x plus 5 over x minus 1, x plus 3. All right, so that is, again, this is our factored form. And we want to find our standard form, so I'm just going to go ahead and distribute and multiply. So that would be 3x plus 15. And in the denominator, if I multiply that up, you can use your box or your distribution, however you want to do it. But I would have x squared plus 2x minus 3. So this would be our standard form. All right, in part B, again, finding that same information. So end behavior, we look at the first terms in our standard form here. So y equals 3x over x squared. That reduces to 3 over x, which means we have a horizontal asymptote at y equals 0. And we can write that as the limit as x approaches both positive and negative infinity for our function g is equal to 0. All right, so that was our end behavior. Next, again, I like to find the wholes. And looking at our factored form, I don't have any common factor, so we would say there are none, there are no wholes. But we can find our vertical asymptotes by taking the denominator. Both of these we can go ahead and use because none of them are part of a whole. So we can go ahead and say x minus 1 equal to 0 and x plus 3 equal to 0. So we have x equals 1, x equals negative 3. So we have 2 vertical asymptotes. And then last is our zeros. So we set our numerator equal to 0, so that factor there, x plus 5 equal to 0. So x equals negative 5. All right, so we have that information. So this, again, is stuff that we've seen, stuff that we've done, and we wanted to do it to just say, we have these two different forms, factored form versus standard form, and to just kind of say, what did the standard form help us to find? So in both of these, the standard form allowed us to easily find our end behavior. So the standard form allowed us to find our end behavior. Let me make that a little bit thicker. End behavior. And then factored form helps us find everything else, right? The wholes, the vertical asymptotes, and the zeros. The end behavior, I'm going to go ahead and say, are horizontal asymptotes. All right, so this again is stuff we've seen, we've done. Haven't really straight out specifically stated it in these terms, but it's things that we've seen, right? Okay, so let's go ahead and move on to the next page. So we have this problem here, problem number 3. We have the graph of a rational function f of x is shown below. We want to write an equation in factored form for f of x. So we want to identify all the key information that we have here, and then how would we put that into a function, right? Into an equation. So we have, let's go ahead and see what we have. We have a vertical asymptote. I see a vertical asymptote at x equals 2. I have a hole here a hole at, what would that be? 1, 2, 3, 4 at x equals 4. That's about, looks like 4 commas negative 0.5. Don't know that for certain. That's what it looks like. We have a horizontal asymptote at y equals negative 1. Okay, I think that's all the key information that we have. We do have a point right here that we might be able to use. We have a 0. Oh, yeah, that's important. We have a 0. Didn't think of that. We have a 0 here at 1, 2, 3, comma 0. 3, comma 0. X equals 3. Okay. So I think we can go ahead and write an equation to help us identify what is going on here. Okay, so let's go ahead and put this all into an equation. So we're going to have f of x equals, and this is a rational function. So let's start putting some stuff in. Vertical asymptote, so that is x equals 2. So if I was to go backwards, that would be x minus 2 equal to 0. So that'd be a factor down in the denominator, x minus 2. That would be a vertical asymptote. And see, we have a hole at x equals 4. Well, that means that I would have had originally x minus 4 equal to 0. Now that would have to be a factor in both the numerator and the denominator, so x minus 4 and an x minus 4 in both the numerator and the denominator. And then it says we have a horizontal asymptote at y equals negative 1. So that means that I should have, in this, y equals, I should have like a negative and then x to the same power in both the top and the bottom, because then that would have canceled out to negative 1. So I need to make sure I have the same power in the top and the bottom. Right now, if I was to multiply these, I would have x squared plus, whatever. And right now, this would just have x to the first. So do I have the same power? I do not yet. But I do have one more piece of information here. I have a 0 at x equals 3. So if I include that, that would be x minus 3 equal to 0. So I should have another factor up in the numerator. All right, now let's check. I have, if I multiply, that would be x squared plus whatever, x squared plus whatever. So I have the same power, but I do not have that negative yet that I want. So I want to go ahead, I want to say that this is just going to be negative 1. That's what looks like what it should be to me. Now, we have to be careful with that, though. I'm going to actually label this as negative a. And that's because we don't know exactly what all is going on yet. So I'm going to actually use this point to figure out what my a is. We did something like this in when we did our quadratics earlier in the year. But so this point is the point 1 comma, let's see, 1 comma negative 2. So we're going to go ahead and use that point 1 comma negative 2 to figure out exactly what would that a value be. Now this is an x value, y value, so that would become negative 2 for the f of x. Remember, f of x is also our y value. And that'll be, so I'm just going to label it as a. Don't know what a is yet. A. and that is going to be 1 minus 3 and 1 minus 4 over 1 minus 2 and 1 minus 4. So we have that this would give us negative 2 equals a times negative 2 times negative 3 over, let's see, negative 1 times negative 3. Okay, so these negative 3's can cancel, which makes sense because that's part of the whole. That whole kind of cancels everything out. And we are left with negative 2 equals a times positive 2. And if we go ahead and we divide, we do check out that a is equal to negative 1. So we can go ahead with certainty now say that our function is going to be the function negative 1 parentheses x minus 3 times x minus 4 over x minus 2 times x minus 4. And we can use decimals or a graphing calculator to double check that, but that should be our function. So to recap, when you are given a graph and you want to write an equation, you want to go ahead and find all those key pieces of information. You're going to go ahead and put it into your function like we see here. But then you don't know what this leading term is, this a value here. So we are going to have to take or find a point on the graph to find out exactly what that point or that value is going to be. So let's go ahead and try one more. We have another problem right here. Let's go ahead and find each of those key pieces of information. So it looks like we have a 2 vertical asymptotes at, so our vertical asymptotes are happening at x equals 0 and x equals 3. So that would give us the factors of x equal to 0, just x, and then x minus 3 equal to 0. So those would be our two factors when we put it into our equation. And then I also see a whole, and this is at the value of x equals 2. And so then that would give us the factor of x minus 2 equal to 0. Let's see, we have vertical asymptotes, we have our whole. We also see, I see an x-intercept, that's important. So a 0 at 1, so at x equals 1, 0.1 comma 0, but x equals 1, so that's going to give us the factor x minus 1 equal to 0. And then I have a horizontal asymptote at y equals 0. So that, remember, that means that in our leading terms, whatever my a and b are, my my higher power needs to be less than the bottom power, so n has to be less than m. So I have to have a higher degree in the numerator. All right, so let's go ahead and build an equation here. So we have f of x, or actually we're using g of x this time. So g of x is equal, and again we're going to have that a to begin with. We're going to have our factors. So let's go ahead and put in those factors. We have two of them, x and x minus 3. So x and x minus 3. Let's see, we also have a whole at x minus 2. So I'm going to go ahead and put that in x minus 2, so top and bottom. Let's see, we have a 0 at x minus 1, so x minus 1. And horizontal asymptote at y equals 0, meaning the top power has to be less than the bottom power. Well, if I multiply all this out, I would have x squared in the top, and in the bottom, if I multiply all that, I would have x cubed. So as of right now, my top power is less than the bottom power, so I'm okay for that horizontal asymptote of y equals 0. But I don't know what my a is yet, so I still need to find a point and plug it in to find out my a. So let's look at our graph and see, is there another point that we could potentially use? It doesn't really look like there's a nice point that we can use. So I'm going to go ahead and pick maybe this one right here. That looks to be about -1, 0.5. Looks to be about there. So we'll get something that's pretty close. It might not be exactly what we have pictured here, but it should be pretty close. So let's go ahead and plug that in and see what we get. All right, let's see. So using the point -1, 0.5, we will have 0.5 or 1/2. I actually might just make that 1/2, the fraction 1/2. And that'll be a, and then -1 minus 2, -1 minus 1, -1, -1 minus 3, and -1 minus 2. All right, so let's go ahead and see what we have. So that should give me 1/2 equal to a, and that will be -3 minus 2 over -1. That will be -4. And then that will be, looks like -3. So again, these -3's should cancel out. And then I should have 1/2 equals a, let's see, -2 over +4. Does that look right? -2 over +4. Okay, so I'm going to go ahead and multiply everything by 4 to get rid of the 4. So that should give me 2 equals -2a. So then I get an a equal to -1. So a negative again, interestingly enough. All right, so then that gives me a function g of x equal to -1, x minus 2, x minus 1, over x times x minus 3 and x minus 2. That is a factored version of that function. All right, so let's go ahead and look at our last couple problems and let's see what we have. So it says sketch a picture of the rational function f of x with the following properties. So limit as we're going to positive and negative infinity is equal to 0. So that means automatically, it says sketch a picture, so I'm going to start putting some of this information in. Automatically, that tells me that I have a horizontal asymptote at y equals 0. So I can go ahead and put that in, horizontal asymptote at y equals 0. And then I have limit as x approaches 3 from the left, 3 from the right, and we're going to infinity. So these two tell me I have a vertical asymptote at x equals 3. So x equals 3, I have a vertical asymptote. Now that is the only information that I am given. And it says work with your group. So this obviously video I can't work with group, but regardless, we're going to come up with a function equation for f of x with these properties. So I'm going to sketch the graph and then come up with a function that could have these properties. So I'm going to have my function going, let's see, so as we come to 3 from the left, we're going down to negative infinity. So I was actually going to start, having it go up like this, but then that would be going to positive infinity. And that's not what it says. It says From the left, we're going to negative infinity. Now, it doesn't tell me I have a 0. I don't have another vertical asymptote, but I do have this horizontal asymptote. So it would make sense for this to kind of just come up alongside like so. All right, so we're going to negative infinity from the left, and then from the right, we're going to positive infinity. So it makes sense for this to be coming down and then going out like this here. All right, so that would be a good sketch of the graph. Now it says that we want to come up with the function equation, so this is going to be just like what we were doing. So identifying all this information. Doesn't give us information that we have a hole. You could include a hole if you want. So say I want, hey, a hole right there. You could. I'm going to make this simple myself though, and I'm going to say there are no holes. Vertical asymptotes, we just have the one at x equals 3. So that gives us a factor of x plus or x minus 3 equal to 0. Do the opposite. Let's see, zeros. Since I have a horizontal asymptote at 0, I'm not crossing it. Technically, I still could, but making this simple myself, I'm going to say that I'm not crossing it. It doesn't give us any information one way or the other. So I'm just going to say that I have no horizontal asymptotes. And then, or no zeros, sorry. And then I do have a horizontal asymptote at the y equals 0. So again, remember that just means that the power in the numerator has to be smaller than the power in the denominator. N needs to be less than m. So let's go ahead and throw this all in to a function and see what we have so far. So f of x equals, we have a, and then times anything in the top. So let's look. Holes, I have none. Okay, so nothing there. Vertical asymptote, I have x minus 3. So I should have an x minus 3 down in the denominator. Zeros, I have none, so I'm not putting anything there. So it actually looks like that's pretty much it. Horizontal asymptote, I can double check that. But I have, that would be x to the 0 power, since I have no x's up there, and this is x to the first. So that definitely matches. My top is less than the bottom, so we're good there. All we need to do is figure out what my a is. Let this look a little bit better. I'm going to put a more like there. So let's pick a point. Looking at my graph the way I sketched it, and again, you might have sketched a little bit differently, but I have a point right here. So I'm going to go ahead and use that one. So 0, negative 1, that y-intercept. All right, so if I use that point, 0, negative 1, I would have negative 1 equals a over 0 minus 3. And so then that would be negative 1 equals a over negative 3. Multiply everything by that negative 3, and I get a equal to positive 3. So that gives me a function f of x equal to 3 over x minus 3. Looks pretty good to me. And we're good. We're done with that problem. All right, so let's go ahead and look at problem number 6. To make this problem work a little bit better, after I'd created the notes, realized that this one, as it is right now, doesn't work out as well as it could. So we're going to go ahead and change just this one here to say that we're going to positive infinity. All right, so just like the last one, we're given this information. And so it tells us that we are, this limit as we're going to positive negative infinity is going to negative 2, telling us we definitely have a horizontal asymptote at x equals negative 2, not negative 1, negative 2. Go ahead and put that into our graph, negative 2, horizontal asymptote. And then these two here, we're going to positive and negative infinity as x goes to negative 1. So definitely tells us that we have a vertical asymptote at x equals negative 1. So let's go ahead and put that in here, x equals negative 1. Now also, from this vertical asymptote, we're told which direction we're going. So on the left, The left, we just changed this. We're going to be going to positive infinity. So we're going to positive infinity on this left-hand side. So I'm going to go ahead and have my graph just kind of come down like this. That looks pretty good there. And then on the right-hand side, we're going down to negative infinity. So on the right, we're going to negative infinity. So going from there, kind of coming alongside like this. Looks pretty good. All right, so from this, we definitely, we're not told about any holes, so I'm not going to include any holes on this one, so none. And then we definitely have that vertical asymptote at x equals -1. So it's -1. So it tells us we have the factor x plus 1 equal to 0. Zeros, since I'm going to positive infinity here, I had to cross the x-axis. You know, I'm alongside -2 here. So I had to cross the x-axis. Now, I could have made this a little bit cleaner, but looks like I'm crossing pretty much at the x value of -1, -1.5, or -3 halves. -3 halves, comma 0. So I'm going to go ahead and just go with that. So we have x equals -3 halves. So how do we get this into that factored form? Well, I can go ahead and multiply everything by 2. I'm just kind of doing the opposite. So 2x equals -3, and then add 3 over, and I get a factor of 2x minus or plus 3 equal to 0. So I'm going to go ahead and use that factor. All right, and so I think we have everything. Just need to address that horizontal asymptote. So horizontal asymptote at y equals -2. So remember that that means that we should have whatever our leading term is, the top degree and the bottom degree should match, and equals n, such that when this all reduces, we are left with -2. So let's go ahead and see what we have. So we are going to, let's see. We are going to have our function f of x equal to a. In the top, we have our 0 of 2x plus 3, that's 0 factor. We had no holes, so nothing in top and bottom. In the bottom, though, we do have x plus 1. Now, just like the other ones that we've done, we want to find that value for a. So we are going to pick a point. So I'm looking at this and I see a point right here. It looks to be -2, 1, -2, 1. So let's go ahead and use that. -2, 1, and see what a value we get. So that would be 1 equals a, and that would be 2 times -2 plus 3 over -2 plus 1. So that will be 1 equals a times, was that -4 plus 3, being -1 over -1. So it looks like a is equal to +1 this time around. Well, that's not too bad. So our function would then be just 1, 2x plus 3 over x plus 1, or just 2x plus 3 over x plus 1. Again, we can check that with the graphing calculator, but that should definitely hold true. Let's go ahead and just on this last one double check that with Desmos and make sure everything is working out the way it should. And you can do this on each of your problems with a graphing calculator or Desmos. Definitely go ahead and put that all in and see what you get. So let's go ahead and put in what we have. So that came out to 2x plus 3 over x plus 1. So f of x equals 2x plus 3 over x plus 1, right? Or x. Did I do that? Oh, so looking at all this is why my graph doesn't match. So this is a good thing. So reason why we want to check. So looking at a graph, obviously it doesn't match with what we have there, and that's because I picked the wrong value. So I used negative 1.5, but if I look at this, so I was counting off from the vertical asymptote going 1.5, but really that is 2.5. So I need to make some adjustments. So let's go ahead and do that real quick. Let's see, so this shouldn't have been negative 3.5. That should be negative, let's see, so that would be 2.5, 5/2, right? So let's go ahead and change that to negative 5/2, which would be, again, just multiply everything by 2. That would be negative 5 right here, which would tell me that should be 2x plus 5. So let's go ahead and make that adjustment. So that'd be 2x plus 5, which would be 2x, or the 2 plus 5, so negative 4 plus 5 here would give me a positive 1, which would mean my a would be negative 1. So let's go ahead and try that. See, does that make a difference? So that would actually become negative 2x minus 3. Let's go ahead and see if I make that slight adjustment, would my graph be what I need it to be? So negative 2x minus 3. That looks better, right? That matches. I have my horizontal asymptote at y equals negative 2. I'm going up to positive infinity, negative infinity right here. I have that horizontal. It's interesting. It still says that my oh, that's why I didn't change this. This should have been plus 5 here. Oh boy, everything's there. But regardless, that should still. So if I change that, so as it had my x-intercept was still negative 1.5. Let's go ahead and make that adjustment so it gets it more what I want, and that is correct, with negative 2, 1 being a point right here. We can see that negative 2, 1, passed through. There we go, negative 2, 1. All right, so everything works out. We still have our vertical asymptote at x equals negative 2, no, not negative 2, negative 1 vertical asymptote, and y equals negative 2 horizontal asymptote. All right. So that concludes this lesson. Thank you for watching and have a great day.